Hey, and welcome to SanfordFlipMath. This is AP Calculus. We are working our way through the Finney, Demana, Waits, Kennedy book for Calculus, 3rd edition. And we are in section 4.2, which is about the mean value theorem for derivatives. There will be another mean value theorem later in the course. And so we're just going to, this video is really going to overview what the mean value theorem is about, and then do some calculations, some applying the mean value theorem, what are the traditional mean value theorem problems, and then a little bit with antiderivatives. So there are some other theorems and corollaries in the section, and they are nothing real seriously deep, just we've talked about those in class, and we'll talk more about those in class as they come up. So mean value theorem, and this is kind of a big deal, is you need to know what this means. So first of all, the conditions for this are we have to be talking about a closed interval, and on that closed interval it needs to be differentiable everywhere on that closed interval. Now, differentiable implies continuous. In order to be differentiable at a point, it has to be, the function has to be continuous at that point. So if it's differentiable on this interval, on the entire interval, then it will also be continuous. Okay, and so if that condition's met, then what this says is the derivative, there is a point where the derivative is going to be equal to the slope. Now again, we talked about this in class, but derivative does mean slope, but this is slope at a point. So there's a spot where the slope of the curve itself will be equal to the slope across the entire interval. Okay, so another way to say it is that the instantaneous rate of change will be equal to the average rate of change. Not everywhere, it's just saying there is a spot. There is a specific x value, c, so in such a way that the instantaneous rate of change will be equal to the average rate of change. Or in other words, the slope of tangent will equal the slope of the secant. Okay, so that's just what it means. Now, I know some of you are a little more visual, so here it is again. Here, so we're talking, and again, this is straight out of the book. We're talking about this interval from A to B. Okay, and so if I find the slope of that line, this is slope like algebra 1. Okay, there's some place on this interval in between that same A and B value. There's some place on this interval where the slope of the tangent line will actually be the same. So if the slopes are the same, then these are parallel. Okay, so that's what it means, and this could be, you know, illustrated, basically the same illustration, but there are lots of ways to do it. It doesn't have to look exactly like that. Okay, so there's some spot on here where if I find the slope of the secant line, and then I look at, I'm looking for the spot where it's going to be about parallel for the tangent line. Okay, so where those two are equal. Okay, so now I want to pop back just for a second. There is a special case of this that's called Rolle's theorem, and this comes up every now and then. And just so you know, the idea here is that if I'm looking at, so the idea is, you know, here's my A and here's my B. So instead of the interval just being any old x and y value, the interval is between zeros of the function, in other words. If that's true, then the slope of that secant line, the secant line is really just the x-axis. So the slope of that secant line would be 0. And similarly then, there's got to be some point along here where the slope of the tangent line would also equal 0. And so the way it's worded is more like, and this was, you know, I guess the original version of this to come out, but the basic way it's worded is if I have an interval between zeros of a function, then somewhere in that interval the slope of the tangent line is 0. Okay? All right, so that's background for that. And then the question becomes, so what? How do we use this? Okay, well, let's look at an example. Okay, so the fairly straightforward example that results from this is, let's say I'm talking about a function, f of x equals 4 minus x squared. And what I want to know is, first of all, is there an x value where f prime of c equals the average rate of change on this interval -1 to 2. Okay, so initially the question is saying, is there an x value? Okay, and if there is, now, so this will be part A, and then part B, if so, find it. Okay, so this is directly a question that is very obviously mean value theorem for derivatives. Okay, so I'm going to do a little sketch, and the rationale for the sketch is I understand things better if I see what's going on. I'm visual, and I know a lot of you are visual as well. So I just want to make sure that we understand what the question is asking. Okay, so this is a graph of y equals f of x, and then from -1, so here's the x value -1, to the x value 2. Now, average rate of change, remember, is slope. So if I draw that in here, now again, we are concerned with this interval between -1 and 2. And then the question's asking us, is there a spot where the derivative is going to be equal to that? And so what I'm actually, as I'm looking at this, what I'm actually trying to do is, see if I can rotate this. Yes, awesome. I'm trying to picture this in such a way. Okay, I gotta learn how to work this thing. Sorry. Okay, this is not working. Yeah, that didn't help, did it? All right, hang on. All right, forget the ruler. Sorry. I'm just going to grab a line, and what we'll do is I want to get what I want is this idea that I need to get this looking parallel. Okay, that's pretty close. I can adjust this a little bit there. And so I want to say, is there a spot where that line, that tangent line, that touches in a single point, is going to be parallel to the secant line? Okay, so is there a spot where the secant line and this tangent line are going to be parallel? That's what I want to do. Okay. All right. So let me just get that out of there because it's really not there. Okay. So am I on a closed interval? Yep. Is this function differentiable everywhere on that closed interval? Yes. If that's true, then I can apply the mean value theorem, and it says, yes, there is a spot where f prime equals that slope. Okay, and so if I'm going to find the value, all I'm going to do is find f prime and make it equal to that slope and solve it. Now, what's funny to me is this is now a problem that we actually did back in chapter 2. It was after, in section 2.4. If you look at the test that we did, there was a test question that was very much like this. And what we found was, first of all, we need a couple of points. Okay, so I'm going to put -1 into the equation, so it's going to be 4 minus -1 squared, so 4 minus 1, which is 3. Okay, I'm going to put 4 minus 2, put 2 in, which is 4 minus 4, which is 0. And then I'm going to find slope. Okay, so the slope of the secant line is 0 minus 3 over 2 minus -3. Wow, that's really bizarre. So this is -3. I'm sorry, 2 minus negative 1. I was anticipating the 3. Sorry. 2 minus negative 1, so negative 3 over 3, which is negative 1. What I want is the derivative to equal that slope. Well, so the slope is that negative 1. The derivative, well, the original function was 4 minus x squared. Okay, so f prime, 4 minus x squared, I'm sorry, f of x, 4 minus x squared, f prime, negative 2x. I want negative 2x to equal that, so x is going to have to equal negative 1 divided by negative 2, which is 1/2. Okay, so what we just found was the value where those things worked. Okay, is there an x value where all this stuff is true? Yes, by the mean value theorem. Okay, the conditions were met. Find the x value. It's x equals 1/2. My work is down there at the bottom. Okay, you can rewind it to see that. Okay. All right, let's do another example. Okay, so the directions for this are state whether the function satisfies the hypothesis of the mean value theorem. In other words, are the conditions met? Okay, so again, the hypothesis of an if-then statement, that's funny, I switched it, MTV. Mean value theorem, there we go. The hypothesis is the if part, in other words, the conditions. And the conditions are, it has to be differentiable on a closed interval. Okay, so again, differentiable on closed interval. Okay, well, we are on a closed interval, and is it differentiable there? Well, the domain for a natural log, the domain for pretty much any log, unless there's some goofiness going on, the domain is x values have to be positive. Okay, well, this one says x minus 1, so the domain for that would be x has to be greater than 1 since it shifted to the right one. Well, this interval is between 2 and 4. That's good. And just a quick sketch just to know what this thing looks like. There's actually a vertical asymptote there, and there we go. Okay, so now the question is, if it is meeting the conditions, if it is meeting the hypothesis, then we're supposed to find that c, that value of c, that on that interval that satisfies the situation, that where f prime is equal to the slope, the average rate of change. So the instantaneous rate of change equals the average rate of change. That's what we're trying to find. Okay, and all you do is find the average rate of change and find the instantaneous rate of change equation, set them equal to each other, and solve. Okay, so in order to find average rate of change, I need a couple of points. Well, so this is going to be the natural log of 2 minus 1, which will be the natural log of 1, and e to the 0, remember this is e to what power equals 1. That was supposed to be a box. Well, e to the 0 power is, okay? And then the next one, we're supposed to find the y value of natural log of 4 minus 1. Well, the natural log of 4 minus 1 is the natural log of 3, which is going to be one point ugly bunch of stuff. I can just write natural log of 3. I would actually like a numerical approximation for that. So 1.098-ish. 0.98612. All right, so anyway, you get the gist. Okay, so now we need to do slope. So slope would be y2 minus y1 over x2 minus x1. So it's 1/2 the natural log of 3, or if you'd prefer, 0.549. Okay, now that's the average rate of change. What I want to do then is set the derivative. Well, if y equals the natural log of x minus 1, then y prime is 1 over the inside. It was natural log, so I don't have to do a log base e of e. So 1 over the inside times the derivative of the inside. Well, the derivative of x minus 1 is just 1. Okay, so I'm going to take 1 over x minus 1 and make it equal to 1/2 natural log of 3 if we're going to do this exact. Or if we're going to do this rounded. I know some of you are going to freak out if I do everything with a natural log floating around in there. 1 over x minus 1 equals the 0.549 forever. Okay, so I'm going to multiply both sides by a common denominator for both sides, which would be 2 times x minus 1. And the goal here is I just don't want fractions. So 2 equals, those 2's divide out, these x minus 1's divide out. So this becomes x minus 1 times the natural log of 3. Now, I could distribute the natural log of 3, but it makes more of a mess. So what I'm actually going to do is divide by the natural log of 3. And then I'm going to add 1 to both sides. So this, right now this is 2 over natural log of 3 equals x minus 1. Sorry, I'm just running out of room because I already wrote the other part of the problem. So x equals 2 over natural log of 3 plus 1. Okay, so this is left exact. There's no way to leave this exact except to leave that ln in there. Okay, and that, just for the record, this is a 1. I know it looks kind of funky there, sorry. Okay, doing the same thing, I'm going to multiply both sides by x minus 1. Okay, so this is 1 equals 0.549-ish x minus 0.549-ish. I'm going to add that to both sides, add the 0.549 to both sides. Okay, and then I need to divide both sides by. Okay, so hang on just one second. I'm typing in the calculator right now. Okay, and then divided by 0.549. Probably worth noting that I actually just stored that number in my calculator, 2.82047. I guess if I'm going 3 decimal places, which is what the AP exam would do, that's it. Just to confirm this, let me do 2 divided by the natural log of 3, be careful with parentheses, plus 1, and I get 2.820, same exact number. Awesome. All right, well, we're going to stop here, and thank you for watching, and we will see you in class playing with and answering more questions about the mean value theorem. Bye-bye.